Look up at the night sky, and somewhere in that glittering expanse lies one of the most breathtaking and enigmatic sights in the cosmos, the Orion Nebula. A swirling cradle of newborn stars, cosmic dust, and radiant gases. It's a place where the universe paints its most vivid masterpieces. But beneath its striking beauty lies something even more extraordinary, a collection of mysteries so strange they defy our understanding of space itself. What if I told you that within this celestial wonderland, there are phenomena so bizarre they seem ripped straight from science fiction? Unexplained bursts of energy, structures that shouldn't exist, and whispers of forces we can't yet name. This isn't just a nebula, it's a cosmic puzzle waiting to be unraveled. Today, we're embarking on a journey deep into the heart of the Orion Nebula to uncover 30 of its most astonishing secrets. From ghostly filaments of gas that move with a mind of their own to colossal stellar explosions that rewrite the rules of physics, each phenomenon we explore will leave you questioning what we really know about the universe. Picture a region where stars are born in violent, radiant collisions, where magnetic fields twist into impossible shapes, and where some scientists believe conditions might just be ripe for life in ways we've never imagined. The closer we look, the more the Orion Nebula reveals itself not as a static painting in the sky, but as a living, breathing entity full of chaos, wonder, and endless surprises. This isn't just a tour of distant cosmic oddities. It's an invitation to witness the universe at its most unpredictable, its most awe-inspiring. Every discovery we make in the Orion Nebula doesn't just add to our knowledge, it challenges it. It forces us to rethink what's possible, and that's what makes this journey so thrilling. Whether you're a seasoned space enthusiast or someone who simply gazes up at the stars with curiosity, these 30 phenomena will change how you see the night sky forever. So buckle up, we're diving into the unknown, and what we find might just leave you speechless. At the heart of the Orion Nebula lies a celestial powerhouse, the Trapezium Cluster. This tightly packed group of young, massive stars isn't just dazzling to look at. It's a cosmic tempest churning out energy so intense it sculpts the entire nebula around it. The stars here are infants by cosmic standards, barely 1 million years old, yet they burn with a ferocity that dwarfs our own sun. Their brilliance isn't gentle, it's a torrent of ultraviolet radiation and supersonic stellar winds tearing through space like a hurricane. What makes these stars so unstable? For starters, they're giants born from chaos. Unlike smaller, steadier stars, their enormous mass means they burn their fuel recklessly, living fast and dying young. Their surfaces are a constant roil of eruptions, ejecting material at speeds reaching thousands of kilometers per second. These stellar winds collide with the surrounding gas, carving out vast cavities and triggering shockwaves that ripple through the nebula. It's like watching a sculptor with a celestial blowtorch shaping the cosmos in real time. But the real mystery lies in their unpredictability. Some flare without warning, brightening dramatically before fading just as quickly. Others hurl out jets of material in random directions, as if governed by forces we don't yet understand. Even their orbits are chaotic, with gravitational tugs occasionally sending one spiraling toward a violent encounter with its neighbors. This isn't just a star cluster, it's a celestial battleground where the rules of stellar behavior seem rewritten daily. And then there's their most profound impact, light. The trapezium's radiation ionizes the surrounding hydrogen gas, making the entire nebula glow like a cosmic neon sign. Without these stars, the Orion Nebula as we know it wouldn't exist. Their energy is the paintbrush, and the nebula is their ever-changing canvas. Yet for all their destructive power, they're also creators. Their violent winds compress nearby gas, triggering the birth of new stars. It's a paradox as old as the universe itself, destruction and creation intertwined in the heart of Orion. Among the Orion Nebula's many wonders, few are as fascinating. or as fleeting as the Proplyds, those enigmatic protoplanetary disks where planets are born. These cosmic nurseries should be serene places where dust and gas slowly coalesce into new worlds, but here they're caught in a celestial crossfire. The Trapezium Cluster's blistering UV radiation doesn't just light up the nebula, it's actively tearing these infant solar systems apart. Picture a sandcastle at high tide, sculpted one moment and erased the next. That's the fate of many Proplyds here, their material evaporating into space faster than planets can form. Yet some aren't just surviving, they're thriving. Take the Proplyd known as 1647, a defiant disk twice the size of our solar system. While others wither, this one gleams like a cosmic shield, its outer layers ionized into a glowing cocoon by the very radiation that destroys its neighbors. How astronomers believe its sheer mass and density create a buffer, a protective barrier against the stellar onslaught. It's a reminder that even in the harshest environments, nature finds a way. What makes these disks so special isn't just their resilience, it's their diversity. Some are edge-on, revealing their layered structure like tree rings. Others face us head-on, showing glowing centers where fledgling stars devour their surroundings. A few even sport twisted spiral arms, hinting at hidden planets already carving paths through the chaos. And then there are the super evaporators, disks so violently stripped by radiation they leave behind ghostly tails, stretching light years across the nebula like cosmic comets. But the real surprise, some Proplyds here are forming planets faster than theory predicts. In calmer regions of space, planet building takes millions of years. Here, intense heat and pressure might be accelerating the process, cramming eons of evolution into centuries. It's as if the nebula's fury isn't just a destructive force, it's a crucible forging worlds under conditions we once thought impossible. These disks are more than just planetary factories, they're time capsules. Each one holds clues to how our own solar system might have looked in its infancy before the planets settled into their orbits. But unlike our quiet cosmic neighborhood, the Proplyds of Orion live on the edge, their fates hanging in the balance between creation and annihilation. Studying them isn't just about understanding distant worlds, it's about glimpsing the violent, beautiful chaos that shaped everything we know. Deep within the Orion Nebula's swirling clouds, a fiery curtain of gas stretches across the cosmos, the Orion Bar. This razor-thin ridge isn't just another pretty feature. It's a cosmic collision zone where the full fury of the trapezium stars smashes into cold molecular gas. Think of it as nature's own laboratory, a place where raw starlight transforms into one of the most vivid light shows in the universe. The bar glows with an eerie luminescence, a neon sign written in the language of atomic physics. But how does this luminous wall defy the darkness? The secret lies in a violent tug of war between light and matter. The trapezium's ultraviolet radiation slams into hydrogen molecules at the bar's edge, ripping electrons from their atoms in a process called ionization. These freed electrons eventually collide with other particles, releasing energy as light, creating the bar's signature glow. But this isn't a uniform wall, it's a layered masterpiece. Closest to the stars, the gas is fully ionized, burning blue-hot. Further in, it transitions into a redder glow where molecules cling to survival, and beyond that, untouched cold gas lurks in shadow. It's like watching sunlight pierce ocean waves, with each layer revealing a different shade of cosmic physics. What makes the Orion Bar truly bizarre is its sharpness. In most nebulae, these transitions are gradual, but here, the boundary between light and dark is startlingly crisp, like a knife's edge. Astronomers believe magnetic fields might be the invisible sculptors channeling the chaos into order. These fields could act like cosmic fences, corralling gas particles into dense sheets that resist erosion. The result, a glowing cliff face that shouldn't exist, standing defiant against the stellar onslaught. And then there's the chemistry. The bar isn't just about hydrogen, it's a factory for complex molecules from carbon monoxide to water and even organic compounds. In its turbulent layers, simple atoms stitch themselves together, forming the building blocks for future solar systems. It's a reminder that destruction and creation are two sides of the same coin in the cosmos. The Orion Bar isn't just a light show, it's a cradle for the very ingredients of life forged in the furnace of starlight. So why does this matter to us? Because this glowing wall is a time machine. The processes happening here mirror those that shaped our own solar system billions of years ago. Every flicker of light, every chemical reaction is a clue to how planets and perhaps even life emerged from the chaos. The Orion Bar isn't just a distant spectacle, it's a mirror reflecting our own origins written in fire and gas. Hidden among the countless stars of the Orion Nebula, one behaves like no other, V1647 Orionis, a celestial chameleon that rewrites the rules of stellar behavior. This young, sun-like star doesn't shine with steady brilliance. Instead, it erupts without warning, surging in brightness by a factor of 100 before fading back into obscurity. Astronomers call it the Great Orion Nebula Variable, and its violent mood swings have left scientists scrambling for explanations. What could possibly cause a star to flicker like a cosmic light bulb? The leading theory points to a feeding frenzy. Like all newborn stars, V1647 Orionis is surrounded by a swirling disk of gas and dust leftover material from its formation. Normally, this material trickles onto the star at a steady pace, but sometimes the disk becomes unstable. Clumps of matter collapse inward, dumping enormous amounts of fuel onto the star's surface in what's known as an accretion burst. The result, a thermonuclear firestorm that lights up the nebula. Imagine tossing gasoline onto a campfire, except here, the flames are hotter than 10,000 suns, and the fuel is a chunk of cosmic debris the size of a solar system. But there's a twist. Not all the star's eruptions fit the accretion burst model. Some flares are too sudden, too asymmetric, suggesting another force at work, magnetism. Young stars like this one are notorious for their tangled magnetic fields, which can snap like rubber bands, unleashing titanic storms of charged particles. These magnetic tantrums might funnel material onto the star in chaotic spurts, creating irregular bursts of light. It's as if the star has invisible cosmic lightning crackling across its surface, zapping its surroundings with unpredictable energy. Then there's the wildcard companions. Some astronomers suspect V1647 Orionis might not be alone. An unseen orbiting partner, perhaps another star or a massive planet, could periodically disturb the disk, triggering feeding frenzies as it swings close. This would explain why the star's eruptions sometimes follow rough timetables, flaring every few decades like clockwork. But if there is a hidden companion, it's playing an elaborate game of hide and seek, leaving only subtle gravitational clues in its wake. What makes this star truly remarkable isn't just its volatility, it's what it represents. V1647 Orionis is a living fossil, a snapshot of what our own sun might have been like in its violent infancy. Every eruption, every flicker is a window into how stars grow up, how they interact with their surroundings, and how they shape the planets that orbit them. Studying this stellar rebel isn't just about solving a cosmic mystery, it's about understanding the chaotic birth cries of every star in the universe. And with every unexpected flare, it reminds us that even in the vast, orderly cosmos, there's always room for a little anarchy. If you thought cosmic violence was limited to exploding stars, the Orion Nebula has a surprise for you. High-speed bullets of gas tearing through space at over 400 kilometers per second. These aren't metaphors, they're literal projectiles, some stretching twice the length of our solar system, leaving behind glowing shock waves like cosmic contrails. Dubbed the Orion Bullets, these bizarre structures were first spotted in the 2000s, and their origins remain one of the nebula's most electrifying mysteries. So where do these celestial bullets come from? The leading theory points to an invisible troublemaker, a deeply embedded young star hidden behind thick curtains of dust. Unlike stable stars, newborns often go through violent growing pains, ejecting material in erratic outbursts. Picture a toddler throwing a tantrum, except here, the tantrum involves enough energy to launch gas clouds at speeds rivaling asteroid impacts. These eruptions, known as protostellar jets, act like cosmic railguns, accelerating pockets of gas to unimaginable velocities. When these jets slam into slower-moving nebula material, the collision creates the bullet-like shapes we observe, their tips glowing fiercely from the friction of interstellar travel. But here's where it gets weirder. The bullets aren't just moving fast, they're accelerating. Normally, anything hurled through a nebula would slow down due to drag, like a rock tossed into water. Yet these projectiles seem to gain speed as they travel, defying expectations. Some researchers speculate magnetic fields are the invisible engines here, channeling energy into the bullets like cosmic afterburners. Others propose the bullets are actually dense knots of gas, plowing through the nebula and sweeping up material in front of them, creating a snowball effect. Then there's their composition. Unlike the surrounding hydrogen-rich nebula, the bullets are packed with iron and nickel elements typically forged in stellar cores. This suggests they might be debris from an ancient, shattered star, or perhaps material dredged up from deep within their protostellar source. Either way, their presence hints at a turbulent history where elements born in stellar furnaces get recycled into new cosmic ammunition. What makes the Orion bullets more than just a spectacle is their role as architects. As they pierce the nebula, their shockwaves compress nearby gas, triggering waves of star formation in their wake. They're both destroyers and creators, carving new paths through the chaos while sowing the seeds for future solar systems. Studying them isn't just about solving a puzzle, it's about witnessing the raw, unbridled forces that shape galaxies. And with every new observation, they remind us that even in the vast quiet of space, violence can be a catalyst for birth. Amid the Orion Nebula's luminous chaos, dark tendrils slither like cosmic serpents, the enigmatic dark lanes. These dense, twisting corridors of dust aren't mere shadows. They're towering cliffs of soot and frozen gas, some stretching trillions of kilometers tall. While the nebula's glowing gases dazzle with color, these lanes swallow light whole, carving stark silhouettes against the stellar backdrop. But here's the twist: these apparent voids are anything but empty. They're the nebula's skeleton, revealing secrets about its hidden depth and structure that visible light alone could never uncover. Peering into these dark fractures is like holding an X-ray to the cosmos. Because the dust blocks shorter wavelengths of light more effectively than longer ones, astronomers can map their density and distribution by studying how different colors fade behind them. It's a celestial game of shadow puppetry, where the shapes cast by starlight betray the true contours of the nebula's three-dimensional landscape. Some lanes appear razor-thin when viewed head-on, only to reveal their true scale when seen edge-on, like a sheet of paper turned sideways. Others twist into impossible knots, hinting at violent collisions between gas streams or the gravitational tug of unseen objects lurking within. The most striking of these structures is the fish's mouth, a jagged rift near the trapezium stars. From Earth, it looks like a simple dark patch, but in infrared light, it unravels into a labyrinth of filaments, each one a thread in the nebula's tangled web. These dust lanes aren't static, they're dynamic rivers of material, funneling gas toward star-forming regions or shielding fragile protoplanetary disks from lethal radiation. In some spots, the dust is so thick it muffles the nebula's glow entirely, creating pockets of eerie silence amid the stellar fireworks. What's truly astonishing is how these dark lanes defy expectations. Conventional models assumed they'd be smooth, like stirred coffee creamer. Instead, high-resolution images show they're clumpy and fractal, more like a plume of smoke than a uniform curtain. This suggests turbulence rules here: magnetic fields, stellar winds, and gravity all wrestling for control, shredding the dust into intricate patterns. Some lanes even glow faintly in submillimeter wavelengths, warmed by hidden young stars or the nebula's ambient heat, proving darkness isn't always cold. Far from being mere absences of light, these lanes are active players in the nebula's drama. They're nurseries for complex molecules, shields protecting nascent solar systems, and cosmic signposts pointing to the forces shaping Orion's evolution. Every shadow they cast is a clue, a piece of the puzzle reminding us that even in the brightest corners of the universe, darkness holds its own revelations. Scattered across the Orion Nebula like cosmic graffiti, violent jets streak through space. These are the Herbig-Haro objects, nature's own neon signs signaling the birth of stars. Named after astronomers George Herbig and Guillermo Haro, these eerie structures aren't stars or gas clouds, but something far more dynamic: supersonic shockwaves blasted into existence by newborn stars. Picture a stellar tantrum of epic proportions, where fledgling suns eject material at speeds nearing 500 kilometers per second, slamming into the surrounding nebula like interstellar freight trains. The result: glowing, twisted ribbons of gas that unravel across light years, sculpted by forces we're only beginning to understand. Among the most striking examples are HH1 and HH2, a pair of celestial fireworks locked in a cosmic dance. Hubble images reveal them as intricate knots of ionized gas, their bow shocks glowing fiercely where stellar jets collide with slower-moving material. But here's what makes them extraordinary: these twins aren't mirror images. HH1 blazes with a sharp, arrowhead shape, its jet punching through space with surgical precision. HH2, meanwhile, is a tangled wreckage of bubbles and filaments, as though the jet hit a celestial speed bump and fragmented. This asymmetry isn't chaos, it's a clue. The differences trace back to the environments each jet encountered, mapping the nebula's invisible density variations like a cosmic sonar. The engines behind these jets are protostars, stellar infants so young they're still swaddled in gas. As these stars form, their powerful magnetic fields funnel material into bipolar jets, channeling energy away from their cores like pressure valves. But the real magic happens where these jets meet the nebula. Gas atoms, stripped of electrons by the violence of impact, glow with telltale colors. Oxygen burns blue-green, sulfur radiates red, turning each collision into a spectral fingerprint. These hues aren't just pretty, they're data. By analyzing them, astronomers can clock the jet speeds, densities, even the wobbles, hinting at unseen planets tugging at their protostars. Yet the biggest surprise isn't their power, it's their impermanence. Unlike the nebula's grand structures, Herbig-Haro objects are fleeting. Within a few thousand years, their jets will shift direction or fade entirely as their parent stars mature. Some, like HH34, already show this evolution, with older lobes dimming as fresh ones ignite nearby. It's a reminder that star birth isn't a single event but a series of eruptions, each outburst rewriting the landscape around it. What makes these objects more than just celestial curiosities is their role as cosmic sculptors. Their shockwaves compress nearby gas, triggering new rounds of star formation even as they fade. They're both destroyers and midwives, their violence seeding future generations of stars. Studying them isn't just about decoding stellar infancy, it's about witnessing the chain reaction of creation that shapes galaxies. And in Orion's turbulent nursery, they're the brightest, loudest evidence that the universe never builds in silence. Beneath the Orion Nebula's glittering facade lies a shadowy giant, the Orion Molecular Cloud One, a monstrous reservoir of gas and dust so dense it defies imagination. While the nebula's glowing tendrils steal the spotlight, this colossal cloud is the unseen engine driving its evolution, stretching dozens of light years across and weighing in at thousands of times the mass of our Sun. It's not just a backdrop, it's a cosmic womb, birthing stars at a ferocious pace. To grasp its scale, picture our entire solar system as a grain of sand. The Orion molecular cloud one would then span the length of a football field, its dark folds hiding countless stellar embryos. Unlike the nebula's ionized gases, this region is cold bitterly so, with temperatures plunging near absolute zero. Here, gravity works in slow motion, coaxing atoms together over millennia until pockets collapse into protostars. But don't mistake this tranquility for inactivity. Peer deeper with infrared or radio telescopes, and the cloud reveals itself as a war zone of creation, where newborn stars flicker to life like fireflies in a thunderstorm. What makes this cloud extraordinary isn't just its productivity, it's its layered chaos. The outer edges are being blasted by the trapezium star's radiation, evaporating like fog under a blowtorch. Yet deeper in, shielded by dust so thick it could swallow entire solar systems, stars form in relative peace. This duality creates a feedback loop of destruction and renewal. As radiation erodes the cloud's surface, it compresses inner regions, triggering fresh rounds of star formation. It's a cosmic conveyor belt where the nebula's visible brilliance is merely the byproduct of this hidden factory's labor. The cloud's chemistry is equally astonishing. Within its frigid depths, simple molecules like hydrogen pair up to form complex organic compounds, methanol, formaldehyde, even sugars. These ingredients don't just build stars, they're the raw materials for future planets and potentially life itself. Recent observations have detected ethyl alcohol here, enough to fill a trillion cocktails floating in vast molecular waves. Far from a sterile void, this cloud is more like a sprawling interstellar brewery, distilling the universe's building blocks in its icy vaults. But the most tantalizing secret, the cloud star formation isn't uniform. Some zones erupt with stellar births while others lie eerily quiet. Astronomers suspect hidden triggers, perhaps shock waves from ancient supernova or the gravitational nudges of passing stars, act as cosmic alarm clocks, waking entire clusters of protostars at once. This would explain why some areas, like the Kleinman Low Nebula within the cloud, resemble a stellar fireworks display, packed with young suns still wrapped in their dusty cocoons. The Orion molecular cloud one isn't just shaping the nebula we see today, it's writing its future. Every star born within its folds will one day light up new pockets of gas, carving fresh cavities and igniting secondary nebulae. And when the trapezium stars eventually exhaust their fuel, it's this cloud's remaining material that will birth the next generation of cosmic giants. In the grand timeline of the universe, the Orion Nebula is but a fleeting spark, but its molecular cloud, that's the tinderbox ensuring the fire never truly dies. If you think the Orion Nebula's visible beauty is breathtaking, just wait until you see what's hiding in the dark, because some of its most spectacular secrets only reveal themselves in infrared. Beyond the glowing gas and glittering stars lies an entire hidden universe, a place where dust clouds part like stage curtains to unveil a cosmic circus of stellar drama. At the heart of this infrared spectacle is the BNKL region, a chaotic arena where stars don't just form, they erupt, collide, and rewrite the rules of cosmic physics. Imagine trying to watch a fireworks display through thick fog. That's essentially the challenge astronomers face when studying obscured regions like BNKL with visible light. The nebula's dense dust veils its most violent acts, absorbing starlight and leaving telescopes blind to the chaos within. But infrared light slips through these barriers like a ghost, its longer wavelengths unaffected by the dust that blocks our view. When we switch to this spectrum, the Orion Nebula transforms. Faint smudges become blazing stars, and dark voids resolve into swirling nurseries of cosmic activity. The BNKL region is the crown jewel of this hidden world. Infrared observations reveal it as a graveyard of stellar violence, littered with the debris of a cataclysmic event that unfolded just 500 years ago, a blink of an eye in cosmic terms. Here, multiple massive stars, now invisible to optical telescopes, once clashed in a gravitational melee. The aftermath, a runaway star, dubbed the Becklin-Neugebauer object, rocketing outward at 30 kilometers per second, trailing shockwaves that still ripple through the surrounding gas. Nearby, the Kleinman-Low Nebula glows with the heat of countless young stars buried so deep in dust that without infrared eyes we'd never know they existed. But the real showstopper is the explosive history written in the gas itself. Filaments stretching light years across bear the scars of ancient outflows, their twisted paths hinting at titanic forces unleashed when protostars collided or violently ejected material. Some jets here move so fast they've plowed through the nebula like cosmic bullets, leaving behind bow shocks that pulse with energy. And then there's the heat infrared sensors pick up temperatures in these regions soaring to thousands of degrees, evidence of energy discharges powerful enough to reshape entire swaths of the nebula. What makes this infrared circus more than just a cosmic curiosity is how it challenges our understanding of star formation. Conventional models suggest stars form in relative isolation, gently gathering material over time. But BNKL tells a different story, one of crowded nurseries where gravitational tugs and shoves lead to chaos, where stellar births are more like bar fights than quiet solitudes. This hidden realm proves that the universe doesn't always play by the rules we've written for it. The technology revealing these secrets is just as fascinating as the discoveries themselves. Instruments like the James Webb Space Telescope don't just see infrared light, they decode it, translating wavelengths into colors our eyes can perceive. Every hue in an infrared image is a data point, a clue about temperature, composition, or motion. It's as if we've been handed a decoder ring for the cosmos, uncovering layers of the nebula's story that were literally invisible a generation ago. And with each new observation, we're reminded that the universe always holds more mysteries just waiting for the right light to shine on them. Invisible threads of magnetism weave through the Orion Nebula like a cosmic spiderweb, shaping its destiny in ways the naked eye could never perceive. While we see glowing gas and glittering stars, the real puppet master behind the scenes is the nebula's magnetic field, an immense twisting force stretching light years across space. Unlike Earth's tidy north-south magnetism, this field is chaos incarnate, tangled by the violent birth of stars and the relentless push of stellar winds. But how do we even detect something so elusive? The answer lies in a celestial sleight of hand, polarized light. As starlight bounces off dust grains aligned by magnetic forces, it picks up a subtle fingerprint, a preferential vibration direction that astronomers can measure. It's like watching sunlight glint off a wind-blown wheat field. The way the light dances reveals the hidden currents shaping it. In Orion, these measurements unveil a magnetic landscape both beautiful and bewildering. Near the trapezium stars, the field lines are stretched taut, combed into parallel strands by the hurricane force winds of massive stars. But venture deeper into the molecular cloud, and the pattern dissolves into a turbulent scribble, as if the universe itself couldn't decide which way was up. This magnetic maze isn't just cosmic decoration, it's a star-making blueprint. Where field lines bunch together, they act like cosmic scaffolding, propping up vast pillars of gas against gravity's crushing pull. In quieter regions, they channel material into slender filaments, funneling fuel toward hungry protostars with eerie precision. But when the fields grow too strong, they can also starve fledgling stars, gripping gas so tightly it can't collapse to ignite new suns. It's a delicate balance, this magnetic tug of war between creation and restraint, and Orion's turbulent nursery showcases both extremes, the real surprise. These fields might solve a long-standing mystery, why some parts of the nebula birth stars in frenzied clusters while others lie eerily barren. Computer simulations suggest magnetic, dead zones, regions where the field weakens, could act like cosmic trapdoors, letting gas suddenly collapse into sudden starbursts. Meanwhile, areas with tightly wound fields might remain frozen in time, their gas locked in magnetic stasis for millennia. It's as if the nebula has invisible valves controlling the flow of star formation with unseen hands. But the most mesmerizing effect can be seen in the Herbig-Haro jets, where newborn stars shoot plasma along magnetic highways like beads on a string. These fields don't just guide the jets, they twist them into corkscrews, split them into braids, and occasionally snap like rubber bands, unleashing bursts of energy that send shockwaves rippling through the nebula. Without magnetism, the Orion Nebula's stunning structures, the pillars, the bows, the filaments would simply not exist. They're not sculpted by light or wind alone, but by this invisible force writing its signature across the cosmos. What makes these fields more than just a stellar curiosity is their universality. The same processes at work in Orion likely shaped our own solar system's birth, from aligning the first dust grains to steering comets toward young planets. By decoding this magnetic fingerprint, we're not just reading Orion's history, we're glimpsing the hidden forces that orchestrate star formation across the universe. And with every new observation, we're reminded that the cosmos doesn't just move to the beat of gravity's drum, but to the silent, twisting song of magnetism. Among the Orion Nebula's many celestial fugitives, none are as dramatic as the runaway star's stellar outcasts hurled into the void at speeds that defy gravity's grasp. Take Eerie, a blazing blue giant streaking through space at over 100 kilometers per second. This isn't just a star drifting lazily from its birthplace. It's a cosmic cannonball ejected with enough force to escape the nebula entirely. But how does a star, an object with millions of times Earth's mass, get flung across the galaxy like a pebble from a slingshot? The answer lies in a gravitational crime scene, one that traces back to a violent encounter in Orion's ancient past. Rewind the clock a few million years, and astronomers believe Eerie wasn't alone. It shared its orbit with another massive star, both circling each other in a delicate dance. Then catastrophe struck. A close encounter with a third star, or perhaps a binary pair, disrupted their balance. Gravitational chaos ensued, slingshotting one star inward while hurling the other, Eerie, outward like a celestial boomerang. The energy of this collision was so immense, it didn't just nudge the star. It launched it on an interstellar journey with enough velocity to leave the nebula behind forever. Today, if you trace Eerie's path backward, it points like an arrow straight to the heart of Orion, the site of this ancient stellar showdown. But Eerie isn't the only runaway with a dramatic backstory. Mu Columbi, another high-speed exile, shares nearly the same trajectory, suggesting they were both victims of the same gravitational upheaval. Even more intriguing, the Orion Nebula's Trapezium Cluster may hold the culprits, a group of massive stars whose erratic orbits hint at a long-ago collision powerful enough to send debris flying in all directions. It's like finding scattered bullets and working backward to reconstruct the gunfight. What makes these runaway stars more than just celestial curiosities is the trail of destruction they leave behind. As Eerie plows through interstellar space, its fierce ultraviolet radiation and stellar wind carve glowing tunnels in the gas it encounters, creating ephemeral structures called bow shocks. These shimmering arcs, visible in infrared, mark the star's path like cosmic breadcrumbs. Meanwhile, back in Orion, the absence of these stars has altered the nebula's chemistry and dynamics, proving that even missing actors can shape the story. The runaways also challenge our understanding of stellar evolution. Stars like Eerie burn hotter and die younger than their sedentary counterparts, their violent origins altering their lifespan. Some may even escape the Milky Way entirely, destined to drift forever in the intergalactic void. Yet for all their isolation, they're not truly alone. Each carries the chemical fingerprints of its birthplace, a silent testament to the chaos of Orion's nursery. Studying these stellar fugitives does more than satisfy cosmic curiosity. It reveals the hidden violence underpinning seemingly serene nebulae. Every runaway star is a clue, a remnant of gravitational pandemonium that might otherwise leave no trace. And as astronomers discover more of these speedsters, they're piecing together a startling truth. The universe isn't just a place of slow, graceful orbits. Sometimes it's a demolition derby where stars don't just shine, they flee. Amid the Orion Nebula's vibrant palette of reds and blues, there's a peculiar glow that doesn't quite fit, a ghostly green light clinging to certain regions like cosmic moss. Astronomers once dubbed this the extended green emission, and for years it sparked wild theories from alien signals to unknown states of matter. But the truth behind this eerie radiance is even more fascinating than fiction. It's the signature of complex carbon molecules, the universe's way of scribbling its chemistry in light. The mystery began when telescopes first captured this green haze, distinct from the nebula's usual hydrogen glow. Unlike the sharp emission lines of ionized gases, this light was diffuse, smeared across space like a watercolor wash. Early observers couldn't match it to any known element, fueling speculation. Then came the breakthrough. The glow wasn't from atoms at all, but from vast clouds of aromatic hydrocarbons, giant molecules built from carbon rings drifting between the stars. Picture the soot in a candle flame, but on a cosmic scale, with structures as intricate as snowflakes and as abundant as sand on a beach. How do these molecules light up? The secret lies in their flexibility. When bathed in ultraviolet radiation from nearby stars, their carbon rings vibrate like tuning forks, absorbing energy and re-emitting it as green light. It's a process called fluorescence, akin to how glow in the dark paint charges under a blacklight. But here, the paint is sprawling light years wide, and the blacklight is the fury of newborn stars. The result is a luminous fingerprint revealing where carbon, the backbone of life, is weaving itself into the nebula's fabric. What makes this discovery revolutionary isn't just the presence of these molecules, but their resilience. In the nebula's harsh environment, where radiation shreds most compounds, these carbon structures endure, even multiply. Some theories suggest they form in the winds of aging stars, then hitch rides on comets or dust grains to colonize nurseries like Orion. Others propose they're forged on the spot, assembling atom by atom in the protective shadows of dust clouds. Wherever they originate, their persistence hints at a universe more chemically sophisticated than we ever imagined. And here's the kicker: these aren't just any carbon molecules. Spectroscopy reveals they're polycyclic aromatic hydrocarbons, or complex structures that on Earth are found in everything from petroleum to burnt toast. In space, they're more than curiosities. They're potential building blocks for probiotic chemistry. Some scientists speculate that over eons, these very molecules could drift onto young planets, seeding them with organic ingredients. The green glow in Orion might be more than a pretty light show. It could be a billboard for the universe's hidden potential for life, yet puzzles remain. Why does the emission cluster in certain zones, avoiding others? Why do some regions show spectral quirks, suggesting even larger, weirder molecules? Every answer uncovers new questions, proving that even as we decode one cosmic cipher, the universe is busy writing another. The extended green emission isn't just a scientific breakthrough, it's a reminder that the simplest glows can illuminate the deepest truths. And in Orion's verdant light, we're glimpsing the universe's untold capacity for complexity, one carbon ring at a time. One of the most puzzling mysteries hiding within the Orion Nebula isn't a strange structure or violent outburst, it's a question of time. Stare into its star-studded heart and you'll find a cosmic contradiction. Clusters of stars that, by all rights, shouldn't exist together. Some blaze with the vigor of toddlers, barely 1,000,000 years old, while their neighbors appear ancient by comparison, clocking in at over 10 million years. This isn't just a minor discrepancy, it's a full-blown age paradox that challenges everything we thought we knew about how stars are born. So how do astronomers even measure a star's age? For young stars, it's all about tantrums. Protostars still settling into their new lives flare unpredictably, their surfaces riddled with sunspots and their magnetic fields twisted into knots. They also cling to thick disks of leftover birth material, like children unwilling to let go of their blankets. Older stars, by contrast, calm down, their rotation slows, their disks dissipate, and their light stabilizes. By studying these clues, scientists can estimate stellar ages with surprising precision. But in Orion, the math doesn't add up. The Trapezium Cluster's stars scream youth, their violent outbursts and surrounding Proplyds placing them firmly in the newborn category. Meanwhile, just a stone's throw away, other stars show the serene demeanor of preteens, with none of the chaos expected from their supposed siblings. The implications ripple far beyond Orion. Stellar evolution models honed over decades assume stars in a given nebula form around the same time from the same gas cloud. But if Orion's stars truly span millions of years in age, those models might need rewriting. One radical theory suggests the nebula isn't a single burst of star formation, but a layered timeline, multiple generations born from successive collapses within the same molecular cloud. Picture a cosmic Russian nesting doll, where each wave of star birth triggers the next, compressing gas and igniting fresh stellar nurseries over eons. Another possibility, the older stars aren't Orion natives at all. They could be interlopers drifting in from elsewhere in the galaxy and getting caught in the nebula's gravitational web. Or perhaps our age detection methods are being fooled. Intense radiation from the trapezium might heat surrounding dust, making some stars appear more evolved than they really are. Even magnetic fields could play a role, altering how stars rotate and thus skewing age estimates based on spin rates. Whatever the answer, this paradox reveals a universe more complex than we imagined. If stars can form in staggered bursts within a single nebula, it reshapes how we understand stellar nurseries across the cosmos. And if our measurement tools are flawed, entire chapters of astrophysics might need revisiting. The Orion Nebula's age puzzle isn't just academic, it's a cosmic wake-up call, reminding us that even the brightest stars keep their deepest secrets well hidden. Amid the Orion Nebula's luminous tapestry, some of the most revealing structures aren't the ones that glow, they're the ones that block light entirely. Enter the silhouette disks, eerie dark smudges that stand in stark contrast to the nebula's radiant gas. These aren't empty voids, they're edge on protoplanetary disks, vast rings of dust and debris seen precisely from the side, like holding a vinyl record up to a flashlight. Each one is a cosmic eclipse machine, casting shadows so long they stretch across light years of space, offering us a rare glimpse into the chaotic early days of planet formation. What makes these shadows so special is their composition. Unlike the nebula's diffuse gas, silhouette disks are dense with micron-sized dust grains, particles fine as powdered sugar but dark as charcoal. When backlit by the Trapezium Cluster's intense radiation, they absorb rather than scatter light, creating crisp silhouettes against the glowing hydrogen. Hubble's sharp eye has revealed their intricate structure. Some are razor-thin, others warped or flared, their shapes betraying the gravitational tugs of hidden protoplanets already stirring within. It's like watching smoke curl in a spotlight, except here, the smoke is a future solar system in the making. The most famous of these shadow casters is 114-426, a disk so perfectly edge-on it appears needle-thin. But zoom in and its shadow unveils secrets. The dark band isn't uniform, it's textured with subtle bumps and dips, hints of spiral density waves or perhaps the gravitational fingerprints of infant worlds. Nearby, another disk, 182-403, shows a bizarre hourglass shape, its central region pinched as if by invisible hands. Astronomers suspect this could be the work of a newborn star's magnetic field, funneling material like a cosmic hourglass counting down to planet birth. These disks aren't just curiosities, they're time machines. The conditions within them mirror those of our own solar system 4.5 billion years ago, when the Sun's debris disk birthed planets from similar chaos. The key difference: Orion's disks are drenched in ultraviolet radiation, a harsh environment that should, in theory, strip away their delicate dust. Yet here they are, defiant, enduring. Some even show signs of carbon-rich chemistry, their shadows tinged with the spectral fingerprints of organic molecules. It's a tantalizing clue that planet building might thrive even in the universe's roughest neighborhoods. The real magic happens at their edges. Where the disks meet the nebula's ionized gas, their shadows aren't static. They flicker and shift as stellar winds buffet them. In some cases, the disks act like sails, their material evaporating into space and leaving behind glowing trails reminiscent of comet tails. Others are more resilient, their dense cores stubbornly holding onto enough mass to someday form planets. This interplay of destruction and persistence is what makes silhouette disks so mesmerizing. They're not just passive obstacles to light, but active participants in the nebula's drama. What we're witnessing is a universal story written in shadow. Every one of these disks is a potential solar system in its own right, a future family of worlds waiting to be born. And while most will eventually succumb to the trapezium's relentless radiation, a few, shielded by their own mass or nestled in quieter pockets, might just survive long enough to craft planets. In their darkness, they hold the blueprints for cosmic architecture, proving that even in the brightest corners of the universe, creation often begins where the light stops. Behind the Orion Nebula's dazzling facade lies a hidden labyrinth, the vast, intricate layers of gas known as Orion's Veil. These ghostly sheets, stretching light years across space, aren't silhouettes but illuminated curtains, backlit by stars buried deep within the nebula's dusty folds. Imagine holding a lantern behind a sheer fabric. The patterns that emerge aren't flaws but revelations, tracing the contours of something far larger and more complex than meets the eye. That's the magic of Orion's Veil. It doesn't obscure the nebula's secrets, it unveils them. What makes these layers so extraordinary is their role as cosmic translators. The veil's hydrogen gas absorbs specific wavelengths of light from the trapezium stars, then re-emits them in a softer, redder hue. This process, called fluorescence, transforms the harsh ultraviolet glare into the nebula's iconic glow, like a prism turning sunlight into a rainbow. But here's the twist: the veil isn't uniform. Some patches fluoresce brilliantly, while others remain stubbornly dim, creating a stained glass mosaic of light and shadow. These variations aren't random, they're clues. Brighter regions betray where hidden stars or shockwaves energize the gas, while darker zones hint at dense dust clouds blocking the light entirely. The veil's structure is equally mesmerizing. Far from being a smooth wall, it's a turbulent sea of filaments and bubbles, sculpted by stellar winds and radiation pressure. In some areas, the gas drapes like delicate lace, its threads so thin they'd vanish if not for the starlight piercing through. Elsewhere, it billows into cavernous voids, blown clear by ancient supernova or the relentless push of newborn stars. These features aren't just cosmetic, they're a dynamic record of the nebula's history, etched into the gas-like grooves in a vinyl record. Yet the veil's greatest surprise might be its motion. Spectroscopic studies reveal it's not static but racing outward at tens of kilometers per second, propelled by the combined winds of the trapezium stars. This expansion isn't smooth, it's chaotic, with some regions surging ahead while others lag behind, caught in gravitational eddies or slowed by collisions with denser material. The result, a cosmic ballet of gas where every ripple and knot tells a story of violence and transformation. What does this mean for our view of Orion? The veil acts as both a lens and a filter, softening starlight while selectively amplifying certain colors. Without it, the nebula's core would appear harsher, its details washed out in a searing blue-white glare. But thanks to these layers, we see subtleties, the delicate gradients of ionization, the faintest tendrils of distant gas that would otherwise be lost. In essence, Orion's veil isn't just part of the nebula. It's the reason the nebula speaks to us so vividly across the cosmic void, and there's a deeper lesson here. The veil reminds us that even in astronomy, what we see is never the whole picture. It's a shimmering interface between the visible and the hidden, a reminder that every glowing nebula, every twinkling star is part of a story far richer and far stranger than we could ever perceive with light alone. One of the Orion Nebula's most perplexing puzzles isn't something we can see, it's something we can't. Despite its sprawling size and dazzling brilliance, the nebula weighs far less than it should. When astronomers tally up all its visible components, stars, gas, dust, the numbers don't add up. A significant chunk of mass is missing, lurking invisibly in the cosmic shadows. This isn't just a rounding error, it's a gaping hole in our understanding of one of the most studied regions in space. So where is the rest of Orion's weight hiding? The answer might rewrite what we know about how nebulae and even galaxies are built. The math is straightforward. Based on the nebula's gravitational pull and the motions of its stars, there should be thousands of times more mass than what's visible. That missing material could take two ghostly forms: dark matter or black holes. Dark matter, the universe's most elusive substance, doesn't interact with light but exerts gravitational influence. If woven through Orion's structure, it could explain the discrepancy without leaving a trace. But there's a catch: dark matter is typically found in vast halos around galaxies, not sprinkled inside stellar nurseries. Could this nebula be an exception, or is something else at play? Then there's the black hole hypothesis. Orion might harbor a population of small, hidden black holes, remnants of massive stars that collapsed long ago. These cosmic ghosts would be invisible unless actively feeding, but their gravity would still tug on surrounding stars and gas. Some researchers even speculate about a single, intermediate mass black hole at the nebula's core, a monster several thousand times heavier than our Sun. Such an object could explain why certain stars in the Trapezium Cluster orbit faster than expected, as if whipped around by an unseen anchor, but the truth might be messier. Some of the missing mass could simply be gas too diffuse or cold to detect, hydrogen molecules floating between stars, or dust grains hiding in the darkest corners of the molecular cloud. Others propose exotic possibilities like primordial black holes from the early universe, or even undiscovered forms of matter that behave differently than standard dark matter. Every theory has holes, but each offers tantalizing clues about the invisible scaffolding holding Orion together. What makes this mystery so pivotal is its universal implications. If Orion's missing mass stems from dark matter, it suggests nebulae might be seeded with the stuff from birth, a revelation that could reshape models of star formation. If black holes are the culprits, it hints at a hidden population lurking in similar nebulae across the cosmos. And if the answer lies in plain but overlooked gas, it forces us to rethink how we measure the universe's building blocks. The Orion Nebula isn't just hiding its mass, it's hiding the rules of its own existence. And until we solve this cosmic accounting error, we're left with a humbling truth. Even in the brightest corners of the universe, the darkest secrets remain just out of sight. Hanging in the nebula's glowing expanse like a celestial relic, the bizarre fishhook feature arcs through space with an elegance that defies its violent origins. This crescent-shaped filament of gas, stretching nearly half a light-year across, stands out even in Orion's crowded tapestry, not for its brightness but for its uncanny geometry. Unlike the nebula's chaotic tendrils, the fishhook boasts a smooth, deliberate curve, as if some cosmic angler had cast it into the stellar depths. But this isn't the work of divine fishermen. It's a scar left by astrophysical forces powerful enough to bend space itself. The secret to its shape likely lies in a clash of titanic energies. One theory points to the Trapezium star's relentless stellar winds, which might have sculpted the gas over millennia like a river carving a canyon. Imagine blowing across the surface of a steaming cup of tea. The way ripples form and merge mirrors how these winds could have gradually coaxed the gas into its hooked silhouette. But there's a twist. The fishhook's curvature is too precise for slow erosion alone. Spectroscopic analysis reveals shock waves rippling through its structure, hinting at a more explosive origin. This brings us to the second contender, a supernova's dying breath. When massive stars explode, their blast waves don't radiate evenly. They collide with pockets of denser gas, creating intricate patterns in their aftermath. The fishhook could be a fossilized fragment of such an explosion, its curve tracing the edge of a long-vanished shock front. Supporting this idea are traces of heavy elements like iron and silicon peppered throughout the filament, the telltale ashes of a star that went supernova millions of years ago. It's as if we're seeing the nebula's version of a fossil, preserved in glowing gas rather than stone. Yet the fishhook isn't just a relic, it's an active participant in Orion's drama. Infrared observations show young stars nestled along its inner curve, their birth likely triggered by the compression of gas during whatever event forged the hook. Meanwhile, the structure's outer edge is evaporating under the trapezium's radiation, streaming delicate tendrils of ionized material into space like smoke from a candle. This duality, creation and destruction intertwined, is classic Orion, where even the most serene features seethe with hidden energy. What makes the fishhook truly remarkable isn't just its origin story, but its rarity. While many nebulae sport loops or bubbles, few exhibit such a perfectly defined crook. Some astronomers speculate magnetic fields played a role, their invisible lines acting like wires to twist the gas into shape. Others propose a chance intersection of multiple shock waves, a cosmic coincidence frozen in time. Whatever the truth, this elegant anomaly reminds us that even in the chaos of star birth, the universe occasionally leaves behind signatures of breathtaking precision, a reminder that beauty and violence often share the same celestial stage. Among the Orion Nebula's many surprises, few have baffled astronomers quite like the discovery of an invisible storm, a relentless barrage of X-rays erupting from its youngest stars. When telescopes first turned their gaze toward these stellar infants, they expected to see the gentle glow of warm gas and dusty disks. Instead, they found a fireworks display of high-energy radiation, blazing with the intensity of miniature suns. These aren't the quiet nurseries of cosmic lore, they are battlegrounds where magnetic fields twist and snap like rubber bands, unleashing bursts of energy powerful enough to outshine entire star clusters. The source of this X-ray chaos lies in the turbulent youth of these stars. Unlike our Sun, a relatively stable adult, newborn stars are cosmic toddlers prone to violent tantrums. Their surfaces are racked by colossal magnetic storms, orders of magnitude stronger than anything in our solar system. Picture 1,000 Earth-sized hurricanes colliding at once, their magnetic field lines tangling until they explosively reconfigure in a process called magnetic reconnection. These aren't just theoretical events, they're observable cataclysms, where pent-up energy releases in milliseconds, superheating plasma to millions of degrees and flinging X-rays across the nebula like shrapnel from a stellar grenade. But here's the real shock. These X-ray flares aren't occasional outbursts, they're constant. Some young stars in Orion fire off multiple flares per day, each one packing enough punch to strip atmospheres from nearby planets. The Chandra X-ray Observatory has catalogued thousands of these eruptions, revealing patterns that defy expectations. Smaller stars, once thought too cool for such violence, erupt just as fiercely as their massive siblings. Even more puzzling, some flares originate far above the star's surfaces, in coronas so vast they'd swallow entire planetary orbits. It's as if these stars are wrapped in invisible electric blankets, crackling with energy far beyond what their size should allow. What makes this X-ray frenzy more than just a dazzling spectacle is its impact on planet formation. Protoplanetary disks, those nurseries of future worlds, are bombarded by this radiation, which can ionize gases, alter chemistry, and even evaporate lighter elements before planets can fully form. Some scientists speculate this might explain why gas giants are rare in Orion's vicinity. The very energy-birthing stars could be stifling the birth of certain planets. Yet there's a counterpoint. These same X-rays might kickstart organic chemistry, charging molecules in ways that seed probiotic complexity. The Orion Nebula's X-ray surprise forces us to reconsider the drama of stellar infancy. These aren't serene transitions from dust to star, they're electrified coming-of-age rituals where magnetic violence shapes not just stars, but the fate of everything that might one day orbit them. And with every flare detected, we're reminded the universe doesn't do gentle. Even its youngest lights are born in fire. Rising from the nebula's turbulent sea like skeletal fingers, the Eerie columns known as Orion's finger structures stretch toward the void, their jagged silhouettes etched against the glowing gas. These elongated towers of dust and molecular hydrogen aren't just passive sculptures, they're cosmic survivors, resisting the trapezium star's relentless radiation like desert mesas standing against a sandstorm. Each one tells a story of endurance where gravity and stellar winds wage an eternal tug of war, shaping gas into these haunting forms. But what makes these fingers so extraordinary isn't just their defiance, it's their delicate balance. Too dense to be blown apart, yet not dense enough to collapse into stars, they exist in a razor-thin margin between creation and destruction. At first glance, they might evoke the iconic pillars of creation in the Eagle Nebula, immortalized by Hubble. Yet Orion's fingers are far more dynamic. Where the Eagle's pillars are bathed in relatively gentle starlight, Orion's fingers endure a constant barrage from the trapezium's UV fury, their surfaces boiling away into space like dry ice in sunlight. This violent erosion gives them their signature texture: ragged edges, flaring bases, and translucent tips where gas dissipates into the void. Some even sport glowing caps where the trapezium's radiation ionizes their outermost layers into shimmering shrouds. It's a metamorphosis in real time, with fingers shortening by billions of kilometers every millennium, their material recycled into the nebula's glowing tapestry. But the real magic lies in what these fingers conceal. Infrared telescopes pierce their dusty veils to reveal protostars buried within, cocooned in the densest knots of gas. These hidden nurseries are paradoxes sheltered from the radiation that carved their homes, yet dependent on that same radiation to compress surrounding material and trigger star birth. Some fingers even showcase evaporating gaseous globules, or egg-dense pockets where gas clumps resist evaporation long enough to collapse into fledgling stars. It's as if the nebula's destructive forces accidentally midwifed new life, a twist of cosmic irony written in gas and light. What sets Orion's fingers apart from other nebula pillars is their impermanence. While the pillars of creation may persist for millions of years, Orion's fingers are ephemeral, their forms shifting dramatically within human timescales. Hubble observations compared over decades show visible retreats, their outlines fraying like sandcastles at high tide. This transience makes them invaluable laboratories, offering a front-row seat to the feedback loop between stars and their birth clouds. Every change documents the invisible hand of physics: magnetic fields threading the gas, turbulence rippling through their cores, and radiation chiseling away at their flanks. Yet for all their fragility, these fingers leave a lasting legacy. As they erode, their expelled material enriches the nebula with heavy elements and complex molecules, seeding future generations of stars and planets. They're proof that even in the universe's most violent neighborhoods, destruction and creation are inseparable partners. And as we watch them slowly vanish, we're reminded that the cosmos doesn't build monuments, it writes stories, with every fading gasp of gas a sentence in Orion's ever-evolving epic. Dotting the Orion Nebula like beads on an invisible thread, the enigmatic H2 knots glow faintly against the cosmic backdrop, dense clumps of molecular hydrogen that somehow endure the trapezium star's relentless radiation. These tiny, resilient pockets of gas shouldn't exist here. Bathed in ultraviolet light strong enough to shred most molecules, they cling to existence like dew surviving a desert sunrise, their stubborn persistence rewriting our understanding of how star-forming materials withstand the universe's harshest environments. What makes these knots extraordinary is their simplicity. Each one is little more than a lump of hydrogen gas, chilled to near absolute zero and compressed by gravity into a compact ball. Under normal circumstances, such fragile structures would vanish instantly in the nebula's radiation bath. Yet here they are, dozens of them, some barely wider than our solar system, glowing softly in infrared as they absorb and re-emit starlight. Their survival hinges on a delicate trick of physics: density. While the nebula's diffuse gas evaporates like steam, these knots are so tightly packed that their outer layers act like sacrificial shields, absorbing destructive UV rays while sheltering the cool gas within. It's a cosmic version of an igloo's insulating walls, where the exterior melts to preserve the interior, but the real magic happens inside. Peer into these knots with radio telescopes and you'll find them bustling with activity. Their cores are microcosms of star formation, where gas swirls in turbulent eddies, coalescing into protostellar seeds. Some already flicker with the faint heat of embryonic stars, their gravity growing strong enough to pull in surrounding material despite the external chaos. These knots aren't just survivors, they're incubators, proving that even in the most hostile environments, nature finds a way to forge new suns. Their role in Orion's future is equally fascinating. As the trapezium's radiation continues eroding the nebula, these knots will be among the last structures standing. When the glowing gas dissipates entirely, the H2 knots may remain dark, cold, and silent, but pregnant with stellar potential. Over millions of years, their hidden protostars will mature, eventually igniting and lighting up the surrounding debris with newborn starlight. In this way, the knots aren't just relics of the nebula's past, they're blueprints for its next act, ensuring star birth continues long after the current spectacle fades. What's most surprising is their resilience isn't unique. Similar knots have been spotted in other extreme environments, from the Carina Nebula's violent star clusters to the outskirts of supernova remnants. This suggests a universal survival strategy, a way for star-forming material to endure long enough to birth new generations, even when the cosmos seems determined to erase it. The Orion Nebula's H2 knots are more than curiosities. They're proof that creation persists in the unlikeliest places, and that even in the furnace of stellar radiation, the universe always keeps a few embers glowing, waiting to ignite. Amid the Orion Nebula's swirling tapestry of light and shadow, one feature blazes brighter than the rest: the Bright Bar, a searing ridge of gas that defies the quiet, gradual process we typically associate with star formation. This isn't just another glowing cloud, it's a cosmic pressure cooker where the rules of stellar birth seem to warp under extreme conditions. Stretching over 2 light years, this luminous wall crackles with energy, its surface pockmarked by newborn stars erupting into existence at a pace that leaves astronomers questioning everything they thought they knew about how stars are made. At first glance, the Bright Bar looks like a textbook example of ionization. The trapezium star's ultraviolet radiation slamming into hydrogen gas, stripping electrons and making it glow. But peer closer, and the story unravels into something far stranger. Unlike most star-forming regions where gas collapses slowly under gravity's gentle pull, the Bright Bar is a battlefield of opposing forces. Radiation and stellar winds press inward like invisible hands, compressing gas to densities that should take millions of years to achieve naturally. The result: stars forming in mere thousands of years, a blink of an eye on the cosmic clock. What makes this ridge so revolutionary is its sheer productivity. Telescopes like Hubble and ALMA have spotted protostars here packed so tightly they resemble cosmic beehives, their births accelerated by the bar's extreme environment. Some are swaddled in disks already fragmenting into planetary building blocks, suggesting planets might arise here faster than theory allows. Meanwhile, the bar's outer layers evaporate violently, creating shock waves that ripple back into the gas, triggering yet more star formation in a self-perpetuating cycle. It's as if the universe discovered a shortcut to stellar assembly, one that bypasses eons of quiet condensation for a turbocharged approach. The real puzzle lies in the bar's structure. Models predict such intense radiation should obliterate star-forming gas, not nurture it. Yet the bright bar thrives, its delicate balance of destruction and creation hinging on a hidden scaffold of magnetic fields. These invisible lines thread through the gas like cosmic rebar, providing just enough resistance to channel the chaos. Where fields are strong, gas clumps survive long enough to collapse into stars. Where they weaken, material evaporates into the nebula's glow. This interplay creates a patchwork of star-forming zones, each one a laboratory for how extreme environments rewrite the rules of astrophysics. Perhaps most astonishing are the bar's failed stars, brown dwarfs glowing dimly between its brighter siblings. These cosmic underdogs, too small to ignite hydrogen fusion, shouldn't exist here at all. Their presence hints at a frenzied star-forming process so rushed it leaves behind stellar misfits, like a baker pulling cakes from the oven too soon. For astronomers, these oddballs are gold mines, offering clues about how turbulence and radiation tweak the recipe for stellar mass. The bright bar isn't just challenging models, it's rewriting them. Its existence suggests that star formation isn't a single, universal process but a spectrum of possibilities, shaped by environment as much as physics. In common nebulae, stars may indeed form as textbooks describe, but in places like Orion, where radiation and chaos reign, the universe improvises, crafting stars in ways we're only beginning to decode. Every flicker of light from this radiant ridge is a reminder. The cosmos has more than one way to spark a star. Hidden within the Orion Nebula's radiant chaos lies an invisible powerhouse, a cosmic ray factory churning out some of the most energetic particles in the universe. Unlike the gentle starlight bathing its clouds, these subatomic projectiles race through space at nearly the speed of light, packing enough punch to strip atoms apart with their sheer force. For decades, astronomers assumed such extreme particle acceleration only occurred near supernova or black holes. But Orion's turbulent heart proves nature has more than one way to forge interstellar bullets. The smoking gun emerged when gamma-ray telescopes detected unexpected high-energy emissions from the nebula's core. These brief, intense flashes signaled electrons being whipped to frightening speeds, but by what? The prime suspects: shockwaves from colliding stellar winds. When stars like those in the Trapezium Cluster blast out million-mile-per-hour winds, they don't flow smoothly. Like fire hoses crossed in midair, these supersonic streams slam together, creating tangled zones of unimaginable violence. Where they meet, particles get caught in electromagnetic chaos, bouncing wildly between magnetic field lines until ejected like marbles from a slingshot. The result: protons and electrons accelerated to energies 1 trillion times more powerful than anything produced in earthly particle colliders. Yet there's another, darker possibility lurking in Orion's shadows: the ghosts of dead stars. Supernova remnants are cosmic ray factories par excellence, their expanding blast waves acting as natural particle accelerators. While no recent supernova have been observed in the nebula, radio telescopes have mapped strange, bubble-like structures in Orion's molecular cloud that resemble fossil shockwaves. If a massive star exploded here even 100,000 years ago, its fading echo could still be pumping particles to extreme velocities. The nebula's youth makes this scenario tantalizing. Young star clusters often host unstable behemoths that live fast, die young, and leave behind powerful remnants. What makes this discovery revolutionary isn't just the particles themselves, but their potential impact. As these cosmic rays tear through the nebula, they leave behind a trail of ionized gas and complex chemistry. Some researchers speculate they could catalyze the formation of rare molecules, or even influence the spiral arms of protoplanetary disks. Others warn these high-energy bullets might sterilize fledgling planets before life could gain a foothold. It's a reminder that star formation isn't just about gravity and light. There's an invisible nuclear component, where particles we can't see shape outcomes we're only beginning to understand. The Orion Nebula's cosmic ray factory challenges our cosmic hierarchy. Here, in what we once considered a peaceful stellar nursery, nature engineers particle energies rivaling the universe's most violent objects. Every gamma-ray flash, every twisted magnetic filament rewrites the rules of where and how the universe's most energetic processes unfold. And as detectors grow more sensitive, we're left wondering, if even a nebula can become a particle accelerator, what other cosmic mysteries are hiding in plain sight? The Orion Nebula holds one of its most mesmerizing performances not in starlight, but in shadow, where vast clouds of dust pirouette through space, casting silhouettes that twist and stretch like cosmic puppetry. These dancing shadows aren't static smudges, they're dynamic echoes of motion, revealing structures that would otherwise vanish against the nebula's brilliance. Imagine sunlight filtering through swaying tree branches, their shifting patterns betraying the wind's unseen hand. In Orion, the choreography is far grander, with entire dust clouds, some wider than our solar system, gliding before the trapezium stars, their shadows stretching light years across the gas like celestial sundials. What makes these shadows more than just fleeting art is their scientific value. When Hubble first captured their motion over years of observation, astronomers realized they weren't just seeing dust, they were mapping the nebula's hidden currents. The shadow's paths trace the velocity of otherwise invisible winds, exposing how material circulates between stars. Some drift lazily, revealing slow, cooling streams of gas. Others jerk abruptly, betraying violent collisions with stellar jets or shockwaves from distant explosions. It's like watching smoke in a wind tunnel, where every ripple and swirl becomes a data point in the nebula's turbulent weather system. The most dramatic performers are the flickering giants, shadow-casting clouds so dense they blot out entire star clusters when they pass. One such structure, nicknamed the Veil Dancer, eclipses multiple trapezium stars for decades at a time, dimming their light in slow, predictable waves. Yet, even as it obscures, it illuminates its edges backlit by hidden stars, unveiling intricate filaments and tendrils too faint to spot directly. These shadows aren't voids, they're lenses, bending our attention to details we'd otherwise overlook. Infrared observations add another layer to the dance. While visible light shadows highlight cooler dust, infrared peers through to warmer layers beneath, creating a stereoscopic view of the nebula's depth. Shadows that appear solitary in optical light often splinter into multiple overlapping strands in infrared, revealing the true complexity of these dust structures. Some even shimmer with internal motion, their grains vibrating like cosmic tambourines as they absorb starlight. Perhaps the most astonishing revelation is how transient these features are. Unlike the nebula's grand pillars or loops, which change over millennia, dancing shadows morph within human lifetimes. Hubble's time-lapse sequences show some dissipating entirely within years, their dust evaporated or redistributed by stellar winds. Others emerge unexpectedly as new clouds wander into the trapezium spotlight. This real-time evolution offers something rare in astronomy, a front-row seat to cosmic change where the universe's slow-motion ballet becomes a performance we can witness in a single generation. These shadows do more than fascinate, they challenge assumptions. Their motions reveal pressures and densities that don't match traditional models, suggesting magnetic fields or turbulence play bigger roles than thought. Some shadows even move counter to the nebula's general flow, hinting at hidden vortices or gravitational eddies. Every silhouette is a clue, a dark stroke on the nebula's luminous canvas reminding us that sometimes the most profound truths are found not in what's illuminated but in what's concealed. Deep within the Orion Nebula's radiant expanse, there's a realm where chaos reigns supreme, the turbulent heart of the nebula, a place where stellar winds howl at millions of kilometers per hour and radiation floods space like a cosmic tsunami. This isn't just a stormy corner of the nebula, it's a maelstrom of forces so intense they sculpt the entire region like an invisible hand molding clay. At its center, the trapezium stars act as the conductors of this bedlam, their furious energy blasting outward in all directions, colliding, twisting, and intertwining in a dance of creation and destruction that defies imagination. The violence here is almost incomprehensible. Stellar winds carrying charged particles at supersonic speeds slam into slower-moving gas with enough force to compress it into shockwaves that glow like neon signs. These collisions don't just create heat, they forge new chemistry, ionizing atoms and ripping molecules apart only to reassemble them into exotic new forms. The turbulence is so extreme that simulations struggle to keep up. Even supercomputers falter when trying to model the sheer complexity of these interactions. It's as if the universe set this region to its highest difficulty setting, packing more physics into a single light year than most galaxies contain across their entire breadth. What makes this chaos so mesmerizing isn't just its scale, it's the order hidden within it. Despite the apparent anarchy, patterns emerge. Vast arcs of gas, shaped like bow waves from a ship, trace the paths of the most powerful stellar winds. Filamentary structures, finer than spider silk but stretching for trillions of kilometers, reveal where magnetic fields have braided themselves through the turbulence like cosmic wires. Even the seemingly random flickers of X-rays and gamma rays follow rhythms, their pulses betraying the underlying physics driving the storm. And then there's the sound, or at least what sound would be if space weren't a vacuum. Translating the nebula's motions into audible frequencies reveals a symphony of deep, resonant booms and high-pitched shrieks, a cacophony of pressure waves and magnetic oscillations. This isn't just noise, it's the nebula's hidden language, a soundtrack of forces shaping its future. Some of these vibrations even trigger new star formation, their rhythmic compressions nudging gas clouds past the tipping point of collapse. Yet the most astonishing realization is how fleeting this chaos really is. The trapezium stars are young by stellar standards, and their winds won't blow forever. In a few million years, their fuel exhausted, they'll fade, and the nebula's turbulent heart will quiet. The shockwaves will dissipate, the gas will disperse, and all that will remain is a scattered cluster of stars, some with planets, some alone, each carrying the chemical legacy of this violent nursery. For now, though, the storm rages on, a fleeting masterpiece of cosmic forces that reminds us, creation is never a gentle act. Scattered like faint echoes across the Orion Nebula, ghostly shells of gas drift silently through space, the last whispers of stars that died violent deaths long before human eyes ever turned toward this cosmic wonder. These ethereal outflows, some spanning multiple light years, are the nebula's hidden ghosts, remnants of supernova whose light faded millennia ago. Unlike the nebula's vibrant glow, these structures are subtle, visible only through the delicate dance of light filtering through their ionized edges or the faint ripples they leave in surrounding dust. But make no mistake, their quiet presence tells a story of cataclysmic endings that helped shape the Orion we see today. The most striking of these relics is a nearly spherical bubble known as Orion's fossil blast, a shell of gas expanding at over 200 kilometers per second. Its perfect curvature suggests a single, symmetrical explosion, a massive star's final scream into the void. Spectroscopy reveals traces of iron and silicon in its filaments, elements forged only in stellar cores during a star's last moments. These chemical fingerprints are the smoking gun, proving this shell isn't just random turbulence but the grave marker of a giant that perished in a supernova's fire. Yet what's truly astonishing isn't the blast itself, but its aftermath. As the shockwave plowed through the nebula, it compressed nearby gas, triggering a wave of new star formation in its wake. The very explosion that ended one star's life likely ignited the birth of dozens more. Not all outflows are so orderly. Another structure, dubbed the Shattered Veil, resembles a cosmic spiderweb, jagged filaments splayed in all directions, as if the dying star's explosion encountered pockets of dense gas that fractured its blast wave into fragments. This chaotic debris field now drifts through the nebula like shrapnel from a celestial grenade, its twisted paths mapping the invisible density variations of ancient interstellar space. Some filaments even glow with the telltale pink of hydrogen gas freshly ionized by nearby young stars, proving that even in death, these outflows continue interacting with the living nebula. The real detective work lies in tracing these ghosts back to their origins. By measuring their expansion rates and chemical makeup, astronomers have pieced together a startling timeline. Some outflows predate the trapezium stars by millions of years. This means the nebula's current brilliance is just its latest act, a rebirth following earlier generations of stars that lived fast, died young, and fertilized the cosmic soil with their remains. Their supernova may have even provided the initial kick needed to collapse the original molecular cloud, setting the stage for the stellar nursery we see today. What makes these outflows more than just ancient relics is their ongoing influence. Their shockwaves still ripple through the nebula, stirring up turbulence that shapes newborn stars' trajectories. Their heavy elements, scattered like cosmic shrapnel, enrich the gas clouds where future planets will form. And perhaps most poetically, their light, though faded from visible view, still lingers as radio waves and X-rays detectable to instruments sensitive enough to listen. These aren't just ghosts, they're the nebula's memory, written in expanding gas and fading echoes. And as we decode their stories, we're reminded that even the most violent endings can sow the seeds for new beginnings. The Orion Nebula isn't just a celestial light show. It's a sprawling chemical laboratory, cooking up molecules so exotic they'd stump even the most imaginative chemists. From the simplest water molecules to complex organic structures, this stellar nursery is a factory for the universe's most fundamental ingredients. Floating within its swirling gases are compounds that shouldn't survive the nebula's harsh radiation, yet here they thrive, defying expectations and rewriting our understanding of cosmic chemistry. Take water for starters. You'd expect this life-giving molecule to evaporate under the trapezium star's ultraviolet glare, yet Orion's cooler, dust-shrouded pockets harbor enough of it to fill Earth's oceans billions of times over. Radio telescopes have detected vast reservoirs of water vapor, some swirling in disks around protostars' future solar systems where this liquid might one day pool on rocky planets. But Orion's water isn't just sitting still. In regions where shockwaves rip through the gas, water molecules get smashed apart and reassembled, creating bizarre isotopes and excited states rarely seen on Earth. It's a reminder that even the most familiar substance behaves strangely when forged in the furnace of space. Then there's the carbon. Simple molecules like carbon monoxide pepper the nebula, acting as cosmic thermometers whose radio emissions betray the gas's temperature. But things get far more intriguing when carbon starts linking into chains. Astronomers have spotted cyanopolyenes molecules with backbones of up to 11 carbon atoms, their structures so elongated they resemble molecular fishing lines. On Earth, these compounds are fleeting curiosities destroyed by oxygen. In Orion's oxygen-poor environment, they flourish, hinting at pathways to even more complexity. The real showstoppers, though, are the aromatics. Polycyclic aromatic hydrocarbons, or PAH, sprawl across the nebula like cosmic soot, their ringed structures glowing green under ultraviolet light. These aren't just pollutants, they're potential building blocks for life. Some theories suggest PAHs could have seeded early Earth, delivering carbon frameworks that eventually became proteins and DNA. Orion's versions are especially intriguing, larger and more complex than those found in most nebulae, as if the trapezium's radiation is stitching them into ever more elaborate designs. But the chemical piece de resistance, glycolonitrile, this sugar-related compound detected in Orion's densest clouds, is a direct precursor to ribonucleotides, the molecules that form RNA. Its presence suggests the nebula isn't just making life's raw materials, it's assembling them into configurations eerily close to those needed for biology. Add in detections of methanol, formaldehyde, and even ethyl alcohol, and Orion starts to look less like a sterile vacuum and more like a cosmic stockroom for life's essential ingredients. What makes this molecular menagerie so revolutionary is its resilience. Conventional wisdom held that UV radiation should shatter complex molecules, yet Orion's chemistry thrives in the chaos, protected by dust grains or hidden in gas clumps where reactions unfold in slow motion. Some compounds even form right in the radiation's path, their creation fueled by the very energy that should destroy them. It's a paradox that forces us to reconsider where and how prebiotic chemistry might arise in the universe. The implications ripple far beyond Orion. If complex molecules can form and persist here, in one of the galaxy's most violent nurseries, then the universe might be far more chemically fertile than we ever imagined. Every time we point our telescopes at this swirling cauldron of elements, we're not just cataloging compounds, we're peering into the universe's recipe book, discovering how the simplest atoms combine to create the building blocks of everything from stars to living cells. And with each new molecule identified, the line between chemistry and biology blurs just a little more. Some of the Orion Nebula's most breathtaking performances aren't happening in real time, they're cosmic reruns, delayed echoes of stellar violence playing out across the centuries. These light echoes work like interstellar fireworks, where flares from long-dead stars bounce off distant dust clouds, illuminating them in slow motion for earthly observers. Picture a lightning strike in reverse, first the thunderclap, then the flash, stretched across decades rather than seconds. One of the most dramatic examples unfolded in 2016, when astronomers noticed an eerie glow pulsing through the nebula's dusty veins. After tracing its origin, they made a startling realization: these weren't new flares, but reflections of an eruption from the variable star V1647 Orionis, which had unleashed a titanic outburst back in 2004. The initial blast's light had traveled straight to Earth, while some of its photons took a detour, ricocheting off hidden dust sheets before finally reaching us 12 years later. The result, a ghostly reenactment of the original explosion, painting phantom structures across the nebula that shimmered briefly before fading into darkness. What makes these echoes more than just celestial curiosities is their ability to map the nebula's hidden architecture. As light traverses different dust layers at varying angles, it creates intricate patterns, expanding rings, warped crescents, or shimmering tendrils, each shape betraying the location and texture of otherwise invisible gas clouds. It's like cosmic sonar, where light substitutes for sound waves to chart the depths of interstellar space. In 2022, researchers harnessed this effect to discover a previously unknown dust shell drifting near the Trapezium stars, its existence revealed solely by the way it scattered echoes from a 400-year-old supernova. The real magic lies in their impermanence. Unlike the nebula's enduring structures, light echoes are fleeting illusions. their paths dissolving as dust grains shift or evaporate. Some linger for mere months, others, like the legendary Orion arc detected in infrared, persist for centuries, their slow fade offering a time lapse of the nebula's evolution. Each echo is a snapshot of the past, a chance to witness stellar violence through a cosmic rearview mirror, one that reminds us the universe doesn't just create light but remembers it. Stretching across the Orion Nebula like threads of a colossal spiderweb, faint filaments of gas weave between stars and pillars, a hidden architecture that binds this cosmic tapestry together. These delicate strands form the nebula's cosmic web, intricate highways of molecular hydrogen, and dust so diffuse they're nearly invisible against the nebula's glow. Yet when observed through radio telescopes or infrared sensors, they reveal themselves as a sprawling network, channeling material between star-forming regions with the precision of celestial pipelines. What makes these filaments extraordinary isn't just their scale. Some stretch for dozens of light years, but their uncanny resemblance to the universe's oldest structures. The similarity is no coincidence. Simulations of the early universe, just a few 100 million years after the Big Bang, show matter clumping into vast filamentary networks, the scaffolding upon which galaxies would later form. Gravity drew gas along these threads like beads on a string, concentrating it at intersections where the first stars ignited. Orion's filaments mirror this primordial blueprint, albeit on a smaller scale. Here, gravity and turbulence replace dark matter as the primary architects, but the outcome is eerily familiar. A lacework of gas where density variations dictate where stars will blaze to life. Zoom in on these filaments and the details grow even more intriguing. Some gleam with the soft light of ionized hydrogen energized by nearby stars. Others remain dark and cold, their interiors so shielded from radiation that molecules like carbon monoxide and water ice cling to dust grains like frost on a windowpane. A few even pulse rhythmically, their subtle brightness variations betraying the passage of shockwaves from distant stellar explosions. These aren't static wires, they're dynamic rivers, flexing and twisting as magnetic fields and stellar winds buffet them from all sides. The most startling discovery, filaments in Orion appear to share a universal width, no matter their length or environment. Each thread hovers around 1 light-year across, a consistency mirrored in other star-forming regions across the galaxy. Astrophysicists suspect this uniformity stems from a delicate balance between gravity's pull and turbulence's push, a cosmic tug-of-war that defines the fundamental grain size of star-forming gas. It's as if the universe has a preferred stitch length when weaving these nebulous tapestries, but the real magic happens at the intersections. Where filaments cross, gravity amplifies, funneling gas into dense knots that eventually collapse into protostars. The Trapezium Cluster itself likely owes its existence to such a nodal point, a cosmic busy corner where traffic jams of gas birthed an entire stellar family. Modern telescopes have spotted younger versions of these intersections elsewhere in Orion. Knots of infrared glow marking where the next generation of stars is taking shape, one filamentary thread at a time. What makes this web more than just a pretty pattern is its role as a time machine. By studying it, we're glimpsing a miniature version of the processes that shaped the universe's first structures. The same physics that sculpted galaxy clusters billions of years ago now repeats in Orion's Nursery, offering a lab to test theories of cosmic evolution. Every strand in this web is a reminder, from the largest scales of the cosmos to the intimate details of a single nebula. The universe builds with threads, not blocks, connecting stars, galaxies, and epochs in a single shimmering design. Among the Orion Nebula's countless stars, some behave like cosmic magicians vanishing without a trace. These aren't just dimming variables or stars hidden behind passing dust clouds. These are stellar disappearances so complete, they leave astronomers scouring old photographs, wondering if they ever existed at all. The most famous case happened in 2016, when a star catalogued as N39434, once a modest but unmistakable presence in Hubble images, simply winked out. No explosion, no fading, just an empty spot where a sun had burned for millennia. The leading theory, it may have quietly collapsed into a black hole without the fanfare of a supernova, a phenomenon so rare it challenges our understanding of stellar death. But how does a star skip the explosive finale and vanish? Normally, when massive stars exhaust their fuel, their cores implode under gravity's crush, triggering a supernova that scatters their remains across space. However, in rare cases, theorists suggest a star might implode so completely, especially if it's rapidly rotating or magnetically unstable, that the rebound never happens. Instead, the entire star gets swallowed by its own collapse, leaving behind only a black hole's gravitational shadow. It's like a building demolishing itself so thoroughly, not even dust remains. Not all vanishing acts are so grim. Some stars might be cloaked by an ancient trick of optics, dense knots of dust drifting across our line of sight. Orion's molecular cloud is riddled with these cosmic pebbles, some no wider than our solar system. When one passes directly in front of a star, it can block the light for decades, even centuries. Infrared observations occasionally catch these imposters, revealing their true nature as cold, drifting debris rather than stellar collapses. Yet even these mundane explanations have twists. Some obscuring dust clouds move too fast for ordinary drift, hinting at unseen forces, perhaps rogue planets or magnetic accelerations flinging them across the starscape. The most tantalizing disappearances, though, are those that defy both collapse and occultation. Stars like V386 Orionis didn't just dim, they altered their surroundings before vanishing. Pre-disappearance spectra showed bizarre chemical signatures, as if the stars were shedding layers in violent, asymmetric eruptions. Others left behind glowing shells or X-ray echoes, suggesting they didn't fade quietly but transformed into something we can't yet detect. Could these be stars transitioning into exotic, ultra-dense states beyond neutron stars, or evidence of theoretical objects like quark stars so dense their very atoms collapse into soup? Every vanished star forces us to confront the gaps in our stellar playbook. The universe, it seems, has more ways to erase a sun than we've imagined. And with every new observation, Orion's disappearing acts remind us, even the brightest lights can leave mysteries in their wake. The Orion Nebula may dazzle us now, but its brilliant display is only an ephemeral chapter in a saga spanning millions of years. Like a cosmic hourglass, time is already slipping away for this stellar nursery, its fate written in the very stars it birthed. Within the next 100,000 years, the Trapezium Cluster's most massive stars will exhaust their nuclear fuel, collapsing in spectacular supernova that will blast away surrounding gas with the energy of 1 billion suns. These explosions will trigger shockwaves capable of compressing distant gas clouds into fresh rounds of star formation, even as they erode the nebula's iconic structures. The finger pillars, the bright bar, all will slowly evaporate under the combined onslaught of radiation and stellar winds, their material scattering into interstellar space like sand in a hurricane. Yet the nebula's death throes will birth new wonders. As the trapezium stars die, their explosions will enrich the remaining gas with heavy elements carbon, oxygen, iron, forging the raw materials for future rocky planets. Hidden protostars currently veiled by dust will emerge as the nebula's next generation of luminaries, their radiation carving new cavities and igniting secondary nebulae within the fading glow of their predecessors. Some models suggest this process could create a chain reaction of star formation, with shock waves from each stellar death triggering births farther into the molecular cloud's depths, a celestial domino effect lasting millions of years. The real turning point comes when the nebula's gas reservoir, currently weighing thousands of solar masses, dips below a critical threshold. With too little material left to form new stars, the region will transition from a fireworks factory to an open star cluster, its remaining stars drifting apart as gravity's grip weakens. The Orion Nebula as we know it will vanish, leaving behind a loose sprinkling of stars whose composition tells the story of their violent origins. The brightest among them, like the Runaway Eerie, will have long since fled the scene, their trajectories tracing back to ancient gravitational skirmishes. But the story doesn't end there. Over billions of years, the cluster's stars will disperse along the Milky Way's spiral arms, their once close bonds stretched thin by galactic tides. Some may pass near future solar systems, their light inspiring alien astronomers just as Orion's glow captivates us today. Meanwhile, the heavy elements forged in the nebula's crucible will seed molecular clouds across the galaxy, becoming part of new stars, planets, and perhaps even life. The nebula's physical form is fleeting, but its legacy is eternal. A reminder that in the cosmos, every ending is laced with the promise of beginnings yet unseen. From ghostly filaments to vanishing stars, the Orion Nebula isn't just a spectacle, it's a cosmic laboratory where the universe conducts its most daring experiments. Think about it, 30 phenomena, each more bizarre than the last, all packed into one swirling stellar nursery. The Trapezium Cluster's violent youth, Herbig-Haro jets carving the sky like celestial blowtorches, the Orion Bullets racing through space faster than comets. Every corner of this nebula defies expectations. And let's not forget the eerie green glow of complex carbon molecules, the whisper of missing mass hinting at dark matter or hidden black holes, or those fleeting light echoes replaying stellar explosions centuries after the fact. Orion doesn't just showcase cosmic wonders, it rewrites the rules, proving that star formation isn't a gentle process but a riot of chaos, magnetism, and unimaginable energy. What makes this nebula so special isn't just the spectacle, it's the questions it forces us to ask. How can planets form in the fury of the bright bar's radiation? Why do some stars vanish without a trace? Could those organic molecules drifting through the veil one day seed life elsewhere? Orion doesn't hand us answers, it hands us puzzles, each one a reminder that the universe is stranger, wilder, and more inventive than we've dared to imagine. And that's the real gift of this cosmic cradle. It doesn't just birth stars, it births curiosity. Now it's your turn. Which of Orion's mysteries left you awestruck? Was it the cosmic ray factory churning out invisible particle storms, or the delicate dance of silhouette disks casting shadows light years long? Drop your favorite in the comments. We're all stargazers here, piecing together the universe's grand story one wonder at a time. And remember, Orion's brilliance is fleeting by cosmic standards, but the curiosity it sparks, that's timeless. So keep looking up, keep questioning, and never stop marveling at the fact that even in the vast, silent dark, the universe is always whispering its secrets.